Okay, so I never got that block of time to do the whole thing this weekend, but I'm going to do, I think, one section at a time. So when I finish this section, I will post that, and then if I can get another section done right now, fine. If not, they'll be kind of straggling in. Um, so 3.1, we talked about limits. 3.2, we're going to talk about continuity, which is a very, very strongly related idea. Continuity, in a kind of general sense of things, means you don't pick up your pencil to draw it. So it just, is continually being sketched. Um, the reason that has to do with continuity is because when you have the limit from either side, that means at least there's kind of a connected path to travel on to get near to the point as you get close anyway. So if then the point you come to is a limit, is also the function point, then you could have passed through it, right? So it's like if you've got two mice on the graph on either side and they come to a door, then if the door doesn't have a gap there, then they could just cross over it and it's continuous. So what this means mathematically is that f is continuous at a function c if the function exists there, so there's not a hole or an asymptote, it's defined, and also that the limit exists at the point, so you have these kind of connected paths to it, and that those are the same. So if the mice get to the door, and there is a door, but the door is high above their heads, then they still can't pass through. If it is not continuous, it's considered to be discontinuous. Okay, so here's an example. Looking at A, it looks continuous everywhere. It looks like you could run along it like a road everywhere except for 3. So at 3, there's a hole which is not even filled in anywhere. So in this case, f is not even defined at 3, and that was the first rule, that it has to be defined. So it's not defined at 3, it cannot be continuous at 3, but it does appear to be continuous everywhere else. So you would say this function is not continuous because there's a discontinuity at x equal 3, and it's a hole. Here, the first thing checks out okay. Every place has a function value. It's defined everywhere. But at 0, the limit doesn't exist because the limit from the left is -1 and the limit from the right is +1. So the limit does not exist altogether, so it fails at number 2. This one, the function is defined everywhere, and there's even a limit everywhere because your only questionable spot is right here, and the limit does exist. The limit is -2. The door you come to is at -2. But the function value is not -2. The function value is 1. So this fails at part C of the definition of continuous. This was called a jump discontinuity. This one is a removable discontinuity, which I think we haven't come to yet, but so was the first one actually. If you can redefine a single point or a finite number of points and fix the problem, then they're removable discontinuities. This is removable because I could just say, no, g of 4 will not be 1 anymore. I'm going to change it to -2, and then it's continuous, so I can fix it with a single redefinition. Which brings us to this, removable discontinuity. So we want to look at the graph here, and we want to find the values where the function is discontinuous. So we look at this, and it kind of looks continuous everywhere except these 2 points. At these 2 points, we have a removable discontinuity because the limit exists. It's defined everywhere. That was the first thing to check. It's got a limit everywhere. That was the second thing to check, but the limit does not equal the function values here or here. So those 2 are the problematic places. And then once we find a discontinuity, we want to check the limits from the right and left and put what f of a is. what the limit is. Okay. So my app did not work. Try this again. There we go. Okay, so I have this. So my discontinuities are at -2 and 2. I'm going to do one of these and leave you to do the other one. And of course you can rewind and reference back. So the first thing we wanted to know is what's the limit? As we approach, I'm going to do -2 from the left. So if I'm coming from the left, then the y value is getting close to -1. And then the limit as x approaches -2 from the right. Now I'm going to come from this side, but I'm still going toward -1. So the limit as x approaches -2 is defined because these are the same. So that's -1. But f of -2 is 1. So because -1 does not equal 1, I have a discontinuity because that part C on the definition was that they need to be equal. So you can do this for 2. And then, so we defined continuity by the limit from the left and the limit from the right being equal to the function value. But what if there is nothing on the left or is nothing on the right? So what if my function has endpoints? Like root x has an endpoint at 0. Sometimes we just define things as being only on a given domain. So if you have a closed interval and you're trying to figure out continuity, all you do is you look at pretend those points aren't there, so it's open, check for continuity there, and then to see if it's continuous here, you just use the limit from the right because the world only exists on the right. And then over here, you check continuity from the left because the world only exists on the left. So if there's nothing over here, then I can just check continuity from one side. So I just take the limit from the left and see if it's equal to the function value. Polynomials are always continuous, always. Rational functions, you've probably heard this term before, but a ratio, a fraction, a rational number, is defined to be an integer divided by an integer so long as the bottom one isn't 0. A rational number is a over b, where a and b are both integers. And b is not 0. So you already know this, right? 3/4, 1/3, 5 over 7. Pi over 4 is not rational because pi is not an integer. So this is how we define rational numbers. And integers are kind of the building blocks. I mean, you can say that counting numbers, 1, 2, 3, that those are really the building blocks of all numbers, and they are, but in their simplest form, we should probably just include all integers anyway. Even back in the day when they wanted to know, just count money, they needed to know how much money was owed to them. If they were counting cows or anything. So we want to include the negatives as kind of a basic type of number. Similarly, a basic, very, very basic type of function would probably be a line, but if you want to take the whole group of all of the most basic functions, it's all the polynomials. So a rational function is one where you have p of x over q of x, p and q polynomials, q not 0. So this is not defined where q isn't 0 anyway. So there will probably be x's where q is 0, but q of x can't just be 0 on its own, and it can't be defined where x is 0. So if you have a rational function, then it's still continuous except where q is 0. And there it's not defined, but everywhere else it's continuous. So if you see a polynomial divided by a polynomial, all you have to do for continuity is check the denominator. And then on the polynomials, you don't have to check anything. Square root functions are continuous everywhere that the function is defined. So in a square root function like this one, ax plus b can't be negative, or you can't take the root. So it starts where ax plus b is 0 and goes from there. So all of these places it's continuous, and before that it's just not defined, but it is continuous at the end point as well. So all you have to do is sort out, just like you always would have for domain, you have to check where this is positive, and everywhere else it's continuous. And all of those places it's continuous. So exponential function, continuous everywhere. Exponential function, this a greater than 0 isn't what makes it continuous, it's what makes it an exponential function. A has to be positive and not 1. Because if a is negative, then when you take it to powers, some of them are not defined, some of them are negative, and some of them are positive. So it's a mess. But then if a is 1, then a to the x is always 1. So that's just the line y equals 1. So positive a not equal to 1 are the rules for being an exponential function to start with. And it's continuous everywhere. So a log function, because it's the inverse of an exponential function, the exponential function a has to be positive, and the results are all positive. X can be negative though, because that's the power, so it's okay to take it to a negative power, but a will always be positive and the results will always be positive. Because the log is the inverse of the exponential function, instead of the result always being positive, the thing you plug in always has to be positive. So it's only defined 0 to infinity. This one's defined on all reals and continuous everywhere. This one is defined only on the positives, because you can't take the log of 0 or a negative, but then it's continuous everywhere it's defined. Okay, so when we're looking for discontinuities and we're given a graph, we can usually see them pretty easily, like the ones we've seen before. There's a hole, there's a jump, there's an asymptote. But if you're given by a formula, then you have to kind of look for where the discontinuities are. So if we're looking here, for all values where the function is discontinuous, we kind of had one like this when we were looking at limits. And what happens is that there's a change on absolute value when x is, or when whatever's in the absolute value is 0. So let me talk about the definition real quick. You've probably, at any rate, been told that the definition of absolute value is distance from 0. The technical definition of absolute value of x is piecewise. So if x is at least 0, this function is x. If x is less than 0, this function is negative x. So this is how it's technically defined. And remember when we were looking at limits, if we had piecewise, we had to check all the endpoints. So if you look at this, it's equal to x minus 1 when x minus 1 is greater than or equal to 0, because the thing that goes here is the thing that's inside, right? And it's minus whatever that thing is when that thing is negative. So let me rearrange this in terms of x. This is equal to x minus 1 when x is greater than or equal to 1. And it's equal to negative x minus 1, or 1 minus x, if you want, when x is less than 1. So I just moved these 1's over. Okay, so x minus 1 is greater than or equal to 0 when x is greater than or equal to 1. So this is the definition of that top part. I sometimes fight with that chalk tool. Oh, this is how I should have done this to start with. Oh well. Okay, so this function then, so this was that. So f of x that's equal to x minus 1 over x minus 1 when x is greater than or equal to 1 minus x minus 1 over x minus 1 when x is less than 1. So all I've done is put that divisor on there. Okay. Note, however, x cannot be 1. So note, x can't be 1. That's just a domain issue. Okay, because we can't divide by 0. So this is really kind of strictly greater than. And I can already state that I have a discontinuity at 1 because the function's not defined, but the question didn't actually ask me that, it just asked me about the limit here. So the limit as x goes to 1 of f as it goes from the left is equal to. So if I'm to the left of 1, it means I'm less than 1, so I'm in this part here, then that's the limit as x goes to 1 from the left of negative x minus 1 divided by x minus 1. But if x is going to 1 from the left, then it's not 1. So this is not 0 and this is not 0, but these two numbers are the same. So this is negative 1. The limit as x goes to 1 from the right now I'm bigger than 1 because I'm to the right of 1. So now I'm looking at this one, not that one. So this is x minus 1 over x minus 1. But if x is going to 1 from the right, then it's not 1. So this is not 0 over 0. This is like, you know, a half over a half or a millionth over a millionth. So this is 1. So going back to the question then, the limit as x approaches 1, which is the discontinuity, of f of x is not defined. This is a jump discontinuity. Okay, for this one, we need to find out where it's undefined. So the first thing is I've got a polynomial divided by a polynomial. So that's continuous, this is continuous except where this is 0. So we need to find where this is 0. The first step in factoring is always factor out whatever's common. I'm going to factor out x. So either x is 0 or x plus 1 is 0. If you have a product that's 0, somebody's 0. So we either have x equals 0 or x equal negative 1. So points to ponder. Okay, so first I'm going to do f of x if I have a rational function. I kind of always want to factor it to see if things clean up. So if the top was not factored, I would factor it now, but it is. That I had factored right there. Those two cancel. So this is 1 over x as long as x isn't negative 1, which it can't be because it's not in the domain. So 1 over x is how kind of I can consider the function. So the limit as x approaches negative 1 from the left or right, but of f of x. So let me forget that. Let me just first consider this. The limit as x approaches negative 1 of f is equal to the limit as x approaches negative 1 of 1 over x because this is only a problem at negative 1, it's not a problem approaching negative 1. So this is 1 over negative 1 is negative 1. So that part is done. So now we need to look at the limit as x approaches 0 of 1 over x, and I get 1 over 0 is some kind of infinite, but I'm not really sure if it's infinite or if it's not existing, so I'm going to try from the left. So from the left of 0, this is negative. This thing is always negative. But I'm dividing 1 into more and more and more pieces, so I'm getting, or smaller and smaller pieces, so I'm getting more and more pieces. So this is going to infinity, but from the left of 0, it's always negative. So negative infinity. The limit as x approaches 0 from the right of 1 over x is still being divided into smaller and smaller pieces, so it's still becoming bigger and bigger. But this time, these numbers are all positive. So this is positive, so this is positive. So I get positive infinity. So the limit as x approaches 0 of this function does not exist because it's negative infinity on one side and positive infinity on the other. Okay, so if we look at a piecewise function, then we have to check all the endpoints. So if I look like x minus 1 is continuous, there's nothing to consider just in that. 0 is continuous. There's nothing to consider just there. X minus 2 is continuous, so there's nothing to consider there. But because I'm stopping suddenly and turning into a different function, I have to check these endpoints here. So for this one, the points I need to check are 1 and 4. Okay, so I'm going to take the limit as x approaches 1 from the left. And then I'm going to check the limit as x approaches 1 from the right. And then I'll decide if the limit exists altogether. So the limit as x approaches 1 from the left. If I'm left of 1, I'm less than 1. That's right here. It says x less than 1. So x minus 1 is what I use. So I plug in 1. So I always kind of plug in first, especially when we're looking at polynomials. You plug it in first and then see what happens. Because what I get is just a number, the number 0, then that's the limit. The limit as x approaches 1 from the right. So I'm to the right of 1. All of these are to the right of 1 right here. But as I'm approaching 1, I'm going to get close to 1. At some point, I'm going to surpass 4. So I'll be in this vicinity. So the function is just 0. The limit of a constant is that constant, so that's 0. So this limit exists because these two match. So let's have a look at 4. The limit as x approaches 4 from the left. The limit as x approaches 4 from the right. Limit as x approaches 4. Okay, so from the left of 4, that's less than 4. All of this has points that are less than 4. But eventually I am going to get past 1 as I approach 4, so it's going to be the limit as x approaches 4 from the left of 0, which is 0. Limit as it approaches from the right. Now I'm bigger than 4, that one right there. x minus 2. So I try plugging in and I get just a number, so that is the limit. These are not equal, so this does not exist. Okay, so this one. Okay, so 1 is my only consideration. That's a polynomial, that's a polynomial, those are continuous, except maybe where they abruptly end. So the limit as x approaches 1 from the right, the limit as x approaches 1 from the left, and then the limit as x approaches 1. Okay, so as I go from the right, I'm bigger than 1, so I'm right here. So that's 3 minus x. 3 minus 1 is 2. This one, from the left, less than 1, so up here, of x squared minus x minus 12. So I'm going to just try plugging in 1 squared minus 1 minus 12. Oh, sorry, that's plus. Plus. So negative 10. These are not equal, so this does not exist. Okay, so here's something that, this one's a little bit fun, I think, and then it's the end of the section too. So if you're watching this prior to class, you should try it, see what you come up with, and pause the video while you try it. It's always kind of good actually to pause the video while you try things, because otherwise you might kind of zone out. Okay, so we're trying to find k that makes this thing continuous. Okay, so what I need, this is going to be a polynomial no matter what k I choose. So is that. So these are definitely continuous independent of each other. So the question is just how to fill in the hole at 2. So, I mean, how to define, how to get 2 to come to itself there. So I'm saying this terribly, but 2 is the only consideration. We need the limit as we approach from the left to equal the limit as we approach from the right. And then, of course, we need that to be the function value, but look, the limit from the right is going to be the function value. We can check it, but it's this. If I get this, then I'm done. So the limit as x approaches 2 from the left of f is the limit as x approaches 2 from the left of, if I'm less than 2, then I'm here, so that's kx squared. And I need for that to equal the limit as x approaches 2 from the right of, as x approaches 2 from the right, it's bigger than 2, so that's x plus k. This one is k times 2 squared, and this one is 2 plus k. So 4k is 2 plus k. Subtract k from both sides. And k is 2/3. Okay, so this is the end of continuity. So we had to have a limit exist to be continuous, and we have to be continuous to consider kind of instantaneous rates of change, but first we need to talk about average rates of change. So that'll be the next section, which I won't record right now. I don't have the time, but which I will record as soon as I can. Actually, probably this afternoon.